Hello there, log fans. Welcome to day 35, the last lesson in this unit. Second day using logs to solve problems. And today we're actually going to talk about something that's pretty interesting, applicable, which is logarithmic scales. But before we get to that, we're going to do the 3-minute review, which is to evaluate expressions involving logarithms. And this one, because it's base 10, there's no number there, it's just base 10, I can just fire that right into a calculator. 3.55. Notice that log base 10 is kind of interesting because essentially it tells you how long a number is. Remember, like log base 10, well, that's just 10 to the exponent 1 is 1. It's like there's 1, 0. Log base 100 is 110 squared, so that's 2, and so on. You can kind of get the bigness of a number from its log, right? It's the exponent here. So log of 3512, well, its bigness is kind of 3 decimal places and a little bit of bigness. But we just wanted to fire that into a calculator. This one, log base anything of anything, we can use the change of base formula, right? Log of the power over the log of the base, and that is about 3.3-ish. Here, I'll rewrite it because the hint's kind of in the way for me. What's the opposite operation of taking the log of something? Well, that's taking the exponential function of something, right? The inverse operation is exponential function. So instead of taking the log of both sides, I'm going to take the exponential function of both sides. Now I've got a function and its opposite connected, and I'm left with just the inside x. And here I have 10 to the exponent 5.2. And there I can clunk that into a calculator, right? Use your exponent button, or that button or that button. Use your exponent button, and you get about 158,000 and change. Fine and dandy. Day 2 of problem solving using logarithms. Today we're going to talk about logarithmic scales. These are all logarithmic scales, and this idea of when you go up 1 unit in a log scale, that's not just 1 unit. It's actually many times. For log base 10, it's 10 times the length. There's a couple of videos that hopefully I remember to attach to today's lessons that weren't me, but are great illustrations of this idea of a logarithmic scale. And so hopefully you give those a watch. The first log scale that we were talking about is this idea of pH. pH is actually a measure of the concentration of hydrogen ions in a substance. Okay, there's some pH levels in the hardcover textbook, the older textbook, and it's a logarithmic scale. So the idea of pH from 5 to 6, that's 1 unit in pH, but that's actually 10 times as acidic from one to the next. And so when we compare substances like we will in B, we're actually comparing two substances that are quite a bit difference in pH. Bananas have a hydrogen ion concentration of that, and I don't know how you measure that. You're going to have to ask Miss Hillary. I know very little about chemistry, but I do know stuff about logs, so I can calculate it. I wouldn't know how to measure the hydrogen ion concentration, but I do know that the hydrogen ion concentration is that number there, and then you clunk that into a calculator. That's actually just the number of decimal places for that number that's a power of 10, right? 1, 2, 3, 4, 5, so that's -5. -5 is just a pH of 5. So bananas have a pH of 5. Bananas have a pH of 5. The pH of urine is 6, which is pretty close to bananas. I don't know what that says about bananas or urine. But the pH of lemon juice is 2. how much more is acidic as P is lemon juice. So this one's actually more acidic. It's got a lower pH. And I'm going to show you two ways to do this. And two ways. The first way we'll do it in the video here, and then we'll never do it like that because it's way too hard. So this is the hard way over here. Yeah. Okay, so for urine, for instance, the idea is I could figure out what the hydrogen concentration of these two substances is and then divide. So I am going to do that. So for P, for urine, if I want to find out the hydrogen concentration, well, I'm going to use the formula. And I want to solve for this, right? This is 6. And I want to solve for that. Well, how do I solve for this? Well, I got to get rid of the minus and I got to get rid of the log. So I'm going to divide by 1 on both sides. It's supposed to be a minus. Let me clean that up. Divide by -1. Then to get this on one side, I take exponential function base 10 of both sides. Those cancel. Function and its inverse, and so I get 10 to the exponent -6 on a calculator, or hopefully you don't need a calculator. It's just 6 decimal places. Make sure I don't goof this up. 1, 2, 3, 4, 5, 6. 6 decimal places altogether. And that's for P. For lemon juice, same calculation. I'm going to skip a couple of steps here because we get the idea. This is 2. Divide by -1, and then exponential function base 10 on both sides. I get the hydrogen ion concentration of lemon juice to be 0.01. Now, basically, if I want to figure out how much bigger one number is than the other, I divide, right? If I want, how much bigger is 10 than 2. Well, I go 2 divided by 10 divided by 2, and I get 5. So I took the big number and divided by the small number. Notice this is a lot bigger than that number. I got to figure out how many times. So I'm going to take the big number, 0.01, and divide by the small number. 1, 2, 3, 4, 5, 6 places. And then you clunk that into a calculator. But you should remember, you just move the decimal places when you're dividing powers of 10, and you get 10,000 times. So we'd say lemon juice is 10,000 times more acidic than urine. Now, that's how it works. I'm going to show you the shortcut. And this shortcut way on this side of this line is all I would expect you to do. I can see the pH difference is 4, right? And other log scales will work the same way. This is the pH difference, but on a log scale, it's a factor of 10 for each increase, right? So it's not just 4 times as much, it's 10 to the exponent 4 times as much, and there's the 10,000. A lot easier this way. Okay? Now there are a couple of curveballs on this technique, but we'll see it a couple more times. Loudness. Loudness is measured using decibels. Decibels are a comparison and sound levels. The Sound of Silence is a great Simon and Garfunkel song, by the way. The Sound of Silence. But it's 0 decibels, and a sound 10 times more powerful is 10 decibels. Now, what's weird about this 10 business makes this not quite the same as pH. The function used to compare sound levels, the decibel level is 10 times. We would say since it's 10 times more, it should only be a factor of 1, because if it was 100 times, that would be a factor of 2, because the exponent is 2. But this decibel, and this is what deci means, 10, it kind of messes up with our log scales. And here's the little formula. And this is kind of the I0 is the sound of silence. I guess you could think of that. That's supposed to be, you know, a barely audible sound, barely audible. And we always go back to that value. We always go back and compare all of our intensity levels um, to that level. So this is the sound intensity of the sound we want to measure, intensity of the sound we want to measure, for instance, a hand clap or a yell or a rock concert, and so on. And we always compare it back to the sound of silence, or that it's barely audible, and we want to find out how many more times is intense that sound. And by sound intensity, it's got something to do with units in physics that I've got no clue. For that one, you can ask Miss Stone how they measure sound intensity. A whisper is about 30 decibels, and a rock concert is 120 decibels. How many more times as intense is the sound at a rock concert? Well, you know, I could use the hard way, you know, just this sort of technique, and do a calculation, and divide at the end, divide to figure out how many more times is loud. But I can see the decibel level, decibel difference is 90 decibels. But that 10 makes me cut off the 0. That's the deci part. So it's not that it's 10 to the exponent 90, because the decibels, it's just 9, the factor of 9 more. So it's 10 to the exponent 9 times as loud. But that's a big number, right? 10 to the exponent 9 is 9 zeros. A billion times. A billion times louder. And again, instead of doing the big long calculation, this is enough. Show me the decibel difference, the 120 minus 90, cut off the 120 minus 90, cut off the 0, put it to the exponent 10, and you're good to go. Earthquakes is another log scale. The magnitude of an earthquake has the symbol m, is found using the function, the Richter scale, which I hope you're familiar with. And it compares the intensity back to barely registerable, not barely audible, but barely registers, like shaking on a ground that barely registers. Barely registers. And I is the intensity of the earthquake that we're interested in. And this intensity that we're talking about is the seismographs, right? You've seen on earthquake videos where it's going like this, and this is there's always some activity, but then all of a sudden there's some and then it starts going like that. This is what this is, this intensity. Whatever units that is in, the seismograph is the same units as here. But we're always comparing back to a standard earthquake. This barely registered standard earthquake is, somebody jumping up and down would actually register on a seismograph, I believe. How many times as intense is a magnitude 6 earthquake? And that's a pretty good earthquake. Also in the videos, I've included some videos of taped of earthquakes so you can see, how much damage. It wasn't a 6.0, I think it was a 5.2 or something like that. Richter earthquake would do, and it's in Los Angeles, I believe. So there's always lots of good drama in Los Angeles. So you should watch that video too. It's a bit of fun. All right. Well, if I want to figure out how many more intense this earthquake is, the one that we're interested in, than the one that's standard or the barely registerable one, I got to get rid of this log. So I go base 10 on both sides, right? Base 10 on both sides. That cancels, and then running out of room here. 10 to the exponent 6 is I over I naught. And if I wanted to find this intensity, I'd cross multiply. And I'd see this earthquake is Not just 6 times as intense, but 10 to the exponent 6, 6 zeros, a million times more intense. A million times as intense. More interesting, I think, is to use an idea of some actual earthquakes. The earthquake that caused the tsunami, this is sort of in the Indian Ocean on December 26, 2004. I don't know how many of you remember that, but it was devastating on Boxing Day. It registered 9.3 on the Richter scale, which is quite high. How much more intense was that major earthquake, the tsunami causing earthquake, than one that measures 7.1? And once in a while we'll get one this severe, but not very often. A 7.1 Richter scale earthquake is described as a major earthquake causing serious damage over large areas, and the energy released in that earthquake is equivalent to the largest nuclear weapon ever tested. So the biggest bomb they've ever exploded would be about a 7.1 on the Richter scale. And we want to know how much more intense this tsunami causing earthquake was than the biggest bomb we've ever blown up on Earth. Well, the Richter scale differences, and this one's different than the decibels because there's no 10, there's no decibel. It's not deci Richter scale. It's just the difference in Richter scale is 2.2, so the intensity difference is 10 to the exponent 2.2, and I'm okay with you doing it that fast, and that's about 158. So that tsunami was 158 times as intense as the biggest bomb ever exploded. It is intense. I tell you, my spelling of the word intense is pretty intense. Okay, that is it for Chapter 4. Review, pink sheets, homework, all that stuff.